Alright, and now we're going to pick up where we left off, beginning section 1.4 of Shilov's book, and we're going to prove some properties of determinants. And as I said before, a lot of the proofs in the book are going to rely on Shilov's method for determining the signs of a determinant. We're just going to use the material that we developed previously in a chapter that I just made up called Chapter 0. Where we discuss permutations and that sort of thing. But here we go. We're not going to actually prove a proposition in this, but we're going to talk about a definition here. So, to start off with the definition, let A be an m by n matrix. We define the transpose of A, denoted A with a superscript T, T for transpose, to be the matrix formed by switching the rows of A with the columns of A, resulting in a new matrix of dimension n by m rather than m by n, right? So that is, take a look. A transpose is equal to the transpose of that big old rectangular array of entries. And what happens is we switch the rows, and we switch the rows with the columns. And the result is that matrix there. Note, the first row of the original matrix is now the first column of the resulting transpose matrix. The second row of the original matrix A is now the second column of the transpose matrix. The third row is now the third column, and so on and so forth, to where we have the mth row becomes the nth column. And that's what we have. Alright, so moreover, if we adopt the shorthand A is equal to, and then parenthetically, A sub ij, then we must have A transpose equal to A sub ji. So this is a shorthand that we're using where we're saying A is a matrix and the entries of it look like that, A sub ij. And then if we take the transpose, what we've done is we've switched the subscripts. Okay, so instead of being A sub ij, now it's A sub ji. Okay, that is, when taking the transpose of the matrix A, the element in the ith row and jth column of A becomes the element in the jth row and ith column of A transpose. That's what happens. And just take a look. So here we have the first entry in the row and the mth row. So row m, column 1. Now that's row 1, column m. Right? And the entry in row m, column 2 is now the entry in row 2, column m. Right? And so on and so forth. Don't need to belabor that. Note that the elements of the main diagonal remain in the same position under transposition. So, take a look. Those are the elements on the diagonal. What's happened to them? Well, they've gotten moved nowhere. Okay, this should be relatively obvious since the main diagonal consists only of entries whose subscripts are the same. That is, entries of the diagonal must be in the same column as row. Hence, given any entry A sub ij on the main diagonal, switching subscripts results in the same entry, A sub ij. Or actually, it's not ij, it's A sub ii, right? Because they're the same in the same row and as column. So they don't get moved anywhere. That's the point. Okay, and that's the end of this one. Next time we're going to prove the following property, property 1.41, and this is in the text. Let A be a square matrix, then the determinant of A is equal to the determinant of A transpose. And that's a really important property. But the proof of that's next time, so hope you're ready, and we'll see you there.